Hello. Now, continuing our work in algebra, we're going to be looking at surds today. Now, we've already met surds plenty of times in our time doing maths. They're just where we have square roots of numbers that don't work out nicely. So the square root of 2, the square root of 3, the square root of 5, and so on. Any number that if we put it into the calculator underneath our square root, we don't get out a nice answer. We just get a decimal that goes on and on forever. This is what we call our surds. And it's often useful from a factorizing point of view to be able to recognize where we can break down a complicated looking square root into something multiplied by a surd. And that's what we're going to practice for the most part today. So the first thing to do is if we want to simplify things down into surd form, if we get numbers like the square root of 75 or the square root of 162. What we're going to do is try and spot, and there's no rule for this, this is simply getting used to spotting patterns in numbers, try and spot a perfect square multiplied by another number that gives the number involved. In this case, 75. What could I write 75 as that's a perfect square multiplied by another number? Well, it would be the square root of 25 multiplied by 3. So, as often comes in with these patterns type questions, there is a way of brute forcing this. You can simply try and divide 75 by numbers until you come across one that is a perfect square. And that will be a way of getting around these problems. It's not the fastest, and pattern matching is very important. But if you're stuck in an exam, just start dividing 75 by 2, and then 75 by 3, and then 75 by 4, and then 75 by 5, and see if you get a perfect square out as a result. And then you'll have 25 by 3 will give you 75. Why do we want that? Because we can break this up into two separate square roots multiplied by each other. So this can be written as the square root of 25 multiplied by the square root of 3. This is a fact about square roots that we need to know. Now, I know what the square root of 25 is. It's just 5. So I have 5, a nice number, multiplied by this surd, root 3. And that is what's called surd form. So if you're asked for your answer in surd form, that's what they're looking for. Now, if we try this number here, I've deliberately picked one that might be a little bit harder to spot. So if you started trying to divide in numbers, however, if you divided this by 2 and then by 3 and then by 4, well, you would find out that it was dividing this by 2 will give you 81. What does that tell you? It means that it can be written as 81 multiplied by 2. Now I do exactly the same trick. 81 I recognize is 9 squared. So I'm able to break that up into the square root of 81 multiplied by the square root of 2 is equal to 9 multiplied by root 2. Now just a quick note about the way that I'm writing this, because we know that there are more types of roots than square roots. So if I had something that looked like this, that would mean the 9th root of 2. What number would I multiply by itself 9 times in order to get 2? Which is not the same as what we're doing at all. This means 9 multiplied by the square root of 2. So it's a big 9. It sits out a little bit separate from the square root sign. Just be careful of it. When we're a little bit careless with the way that we write things, it can be easy to get confused. But so long as we know that the little number inside of the tick is what would tell you what type of root it is, and a big number sitting in front of our square root will always mean the number multiplied by the square root or by the surd. Now, in terms of, sorry, there should be a big line through that, not equal to. In terms of situations where we've simplified down and we now have a bunch of stuff involving surds, the surds end up acting pretty much like letters. So you can imagine that this is really an X, and an X, and a Y. And you will be able to do out these problems making that underlying assumption. So what have we got here? We've got two like terms. We have two things involving the square root of 3, and then we have a different type of thing. We have something involving the square root of 5. So we can add up our square roots of 3, our surd form of this, and we have 3 square roots of 3 plus 5 square roots of 3, so we end up with a total of 8 square roots of 3 minus 2 square root of 5. And that's as far as we can go, leaving our answer in surd form. The only point of that example is to highlight that the surds act basically the same as letters in algebra. So if we have the same surd, we can add and subtract our numbers. If we have different surds, we can't add and subtract our numbers, just like if we had different letters involved in algebra. Now, let's combine these two things in this question here. So I have the square root of 32 minus the square root of 50. And I'll be told in an exam style setting to give my answer in surd form, or I might be given an even more specific instruction than that. But if I see something like this in the exam, it's always going to mean the same thing. I'm going to try and break them down into surd form, and then I am going to see if I'm able to add up any like terms. So I start trying numbers that I can divide into 32 to see if I have a factor that is a perfect square. And I find that I get, for root 32, it is 16 multiplied by 2. So 32 is 16 multiplied by 2. 16 is a perfect square, so that's why I like it. And 50 is 25 multiplied by 2. Now I can break these up. So I can break those square roots up. The square root of 16 multiplied by the square root of 2 minus the square root of 25 multiplied by the square root of 2. And I get 4 root 2 minus 5 root 2. And because these have the same surd, they're effectively the same letter, like we would have in algebra. So, they're like terms, we can subtract them, and I end up with minus root 2. Minus 1 root 2 is my final answer. Now, continuing on with this theme, we're going to multiply out our bracket here, and this works exactly the same way as multiplying out brackets usually works. So I am going to take first term in the first bracket, multiply it by the second bracket, second term in the first bracket, multiply it by the second bracket. So I have 3 on 2 plus root 2 minus root 2 on 2 plus root 2. Same as always. Multiplying out, I get 3 by 2 is 6. Plus 3 multiplied by root 2 is just 3 root 2. Behaves very much like a letter. Minus root 2 multiplied by 2 is going to give me 2 root 2. Again, very much like a letter. This is where things can get a little bit different because I have minus multiplied by plus is a minus. Root 2 multiplied by root 2. Well, this is what would I have to multiply by itself to get 2, and this is what I would have to multiply by itself to get root 2. If I multiply them together, I just get 2. But if you find it that difficult to wrap your head around, we do know that multiplying anything by itself is squaring it. So root 2 squared provides the same argument, and we end up with 2. So I would end up with, I have like terms here. I have stuff involving root 2 there. So I have 6 plus 1 root 2. So 6 plus root 2 minus 2. And I have pure numbers, pure normal numbers here, so I'm going to end up with 4 plus root 2 as my final answer here. So you can see they behave a little bit like letters in algebra, and we have to remember that if we square them, we're going to get rid of the square root. Now finally, there's an extremely important thing that we're going to need, and you can make a note to yourselves. This becomes important again in what's called complex numbers. Now we've already kind of touched on complex roots, but this is going to be important again in complex numbers. So you can make a little note to yourself here. This is going to be important later on when we touch on complex numbers, or when we learn about complex numbers. Now, the way that we do this is effectively to create a difference of two squares type situation on the bottom. So rationalizing a denominator means get rid of the surd on the bottom of the line, get rid of the surd in the denominator. So what I'm going to do is create a difference of two squares type situation on the bottom line. This is just creating difference of two squares. That is the entire rationale of why it is I'm doing what I'm doing here. Because I have a minus b multiplied by a plus b, which becomes a squared plus b squared. So I end up with squaring the square root, which gets rid of it, which means that I only end up with nice numbers on the bottom of my fraction. And I have to do the same thing to the top to keep my ratio the same in the fraction. So I multiply this out, I get 4 root 2 plus 12 all over. We can multiply this out the long way, or again, we're doing this because it's difference of two squares, so I'm going to end up with root 2 squared minus 3 squared. This is again dots. This is difference of two squares. I am creating a difference of two squares type situation. Reminder, a squared minus b squared is equal to a minus b multiplied by a plus b. This is our difference of two squares. I'm using that in reverse. I'm creating that situation in order to square the surd here and get rid of the square root on the bottom line. And this is to make my fractions nicer to deal with. And again, will be important much later on when we do complex numbers. So squaring that out, we end up with 4 root 2 plus 12 all over 2 minus 9. So we get 4 root 2 plus 12 all over minus 7. And I can't see any nice factors top and bottom, so that's as far as I am able to go in that question. So that is my rationalizing a denominator. I have gotten rid of the surd on the bottom of the line, which is what we mean by rationalizing the denominator. So you can see this is a bit of pattern matching in terms of identifying perfect squares and then treating the surds pretty much like we treat letters in algebra. And then finally, for rationalizing a denominator, we need to remember that difference of two squares allows us to square both of the terms on the bottom, which gets rid of the surd. So that looks a little bit like a Z. That's supposed to be a 7. So that is what we need for our surd work for now.